Thank you.
Strange top. Kia ora koutou. Welcome to a joint seminar hosted by the Center for Sustainability and the Otago Energy Research Center. It's my great pleasure to introduce Shama Islam. Shama's a senior lecturer in electrical engineering from the University of Deakin, so she's visiting us at the moment, and she's been traveling around the country a little bit. And today, I guess, I understand your interests are in smart grids, the Internet of Things, and energy management more broadly. And today you're going to share some of your research interests around data analytics for intelligent energy systems. So please join me in welcoming Shama.
Thank you. Hello, everyone. To the people in Zoom, just want to double check if you can hear me properly. If not, just let me know that I do something.
We can hear you.
Thanks. I think Sean already introduced me. Just I wanted to mention that I have been awarded Victoria Fellowship in 2019, and this visit is part of my study mission, which was funded by that Victoria Fellowship. So this fellowship was awarded to me for sharing knowledge, new knowledge, and scientific innovations from overseas to the state of Victoria in Australia. So here is a brief introduction about me. So I did my PhD in wireless communications in 2015. Then I joined at Deakin as a lecturer in electrical engineering in 2016. I have undertaken several projects which are funded by the Australian Renewable Energy Agency through my team. In 2019, I have been awarded this Victoria Fellowship. Apart from that, I have been involved in many professional voluntary services, such as if you have heard about IEEE, which is Institute for Electrical and Electronics Engineers, Power and Energy Society. So I have been the chair of the Victorian chapter of that society. And apart from that, from the teaching space, I have been accredited as a fellow of the Higher Education Academy based in UK. So in short, this is my academic career in a nutshell. So how we teach engineering at Deakin University? We are primarily located in the Geelong Warnbons campus in Victoria, which is 1 hour drive, 1 hour 2 minutes drive from Melbourne. We are focused around project-oriented design-based learning. That is, the students learn by doing different projects instead of just the theoretical knowledge. Here are some snapshots of the facility of the university and our lab. A little bit about Geelong. If you have not traveled to Geelong yet, I would definitely encourage you to take this opportunity during summer. It looks really beautiful to travel through the Great Ocean Road, which starts from Geelong. And I have found every corner of Geelong very, very, very beautiful and scenic. Here are some of our projects, which our colleagues have done with different industry partners. For example, AusNet Services is the transmission distribution network operator in Victoria. With them, our colleagues have done bushfire mitigation from electricity networks. With Noja Power, which is a company which designs phasor measurement units from intelligent monitoring units for the distribution network. With them, we have done a project on the intelligent switchgear for monitoring distribution networks. I have done some collaboration with the Geelong City Council, where I have worked particularly in a pilot study of the energy optimization for Geelong households. Apart from that, we have some past projects with DNVGL, where we have worked on the Australian Battery Performance Standard development, and this is currently with Standard Australia. And other than that, we have also worked on different energy efficiency initiatives for different industrial plants, such as this meat processing plant. This is one unique facility which we have in our campus. This is a campus-based large-scale microgrid. This is a 7 megawatt solar energy farm, and we also have a battery storage system which are positioned on the rear of the campus. This is one of the Australia's largest university-based microgrids. And this is designed to supply around 54% of the Warren Ponds campus's current consumption. We also have 0.25 megawatt installation of rooftop panels and battery storages in some of the buildings. And we can monitor the generation, the demand of these buildings through different visualization platforms. So we also have some solar panels set aside for the research project. So if anyone is interested to do some work on the solar panels, do some experiments, or even work with the data from the microgrid, we might be able to share those and do some collaboration on that aspect as well. So why we need data analytics for the intelligent energy systems, and what applications we could have, and how this can be applied to real world examples. So any intelligent energy systems will have a lot of intelligent devices which produce a lot of data. And if we can analyze this data, we can have a lot of information insights which can help with the network performance monitoring, planning, asset management, etc. And we can integrate intelligent applications such as energy forecasting. We can do event detection. In addition, we can improve the effectiveness of the cybersecurity mechanisms. We can add different new applications, which are like energy optimization, peer-to-peer energy trading. Those kind of applications we can integrate in an intelligent energy systems. Basically, we're going to end up with an Internet of Energy Systems, where we have intelligent devices in all aspects of the energy systems: generation, transmission, distribution, and also at the end user side. For example, if we think about the generation side, if we have some kind of IoT-enabled sensor, we can monitor the irradiation, and based on that, we can ensure that the solar array is aligned to correct position so that we have maximum extraction of the renewable energy from there. If we look into the customer side, if we have the energy management system enabled with IoT, we can have some information from the cloud server regarding what should be the best time to turn on the appliances, and we can operate those appliances accordingly for appliance scheduling operations. So different applications are possible with an energy systems, with an intelligent energy systems enabled with a lot of intelligent devices. One possible application is energy forecasting. As you have more and more renewable energy sources coming to the grid, there are more uncertainties involved with them. These uncertainties can cause problems with the market settlements and so on. Advanced data analytics can help with these energy forecasting applications and ensure that we can forecast more accurately even in the presence of uncertainties. One such technique could be the integration of standard probabilistic methods with big data enabled deep learning methods. That is probabilistic deep learning, and we can manage uncertainties using that. These accurate forecasts can help with the better operation planning and management. One of my PhD students is working in this topic, Bayesian deep learning to forecast solar power generation. And we have done this work in a conference, and the extended version is currently under review. So we have used the Ausgrid solar electricity dataset, and we have used 9 months of data for training the model, and then we have tested the model over the remaining 3 months. And we have generated the prediction intervals rather than generating a point forecast for the renewable generation, for the solar generation. We have generated the prediction intervals, which shows the ranges across which these forecasts can lie. The first figure on the left shows the 48 time steps ahead forecast. And this second figure, this shows the prediction intervals for the entire test data of 3 months. And you can see that if you look into the ground truth and the predictive mean, they are following quite good. They not only can predict the peaks, but it can also predict the smaller generation periods. So just a moment. So is it possible to hide this one? Because then, because some of the writings have gone under that. So thank you. Okay. So in terms of the network performance monitoring, as we have more and more renewable energy sources, our distribution network is facing more challenges to ensure that the network voltages remain within the standard limits. Because we're still using the same old infrastructure, and the companies may not be willing to invest more as we are having more and more renewable penetration. So what we can do, if we have the intelligent phasor measurement units across the distribution network, we can monitor how does the network voltage, current, frequency, these change over time with different levels of renewable energy penetration. So if we can get the renewable energy generation data based on the postcode levels, and we can get the network performance data from the different PMUs, we can develop a correlation between renewable generation and the voltage. And to be specific, we can create a number of voltage indices, which shows like if this index violates by more than 5% or so, then there is a problem, and then the company should look more into this. In terms of data analytics, we can have machine learning models incorporated so that we can predict when these voltage indices are going to be violated if we have some forecasts on the renewable generation data. We can also do post-event analysis. So if some critical network event has happened, then we can associate those voltage performance indices with the different critical network events, how they change with each other and so on. So we have applied these in a project which involved the Australian medium voltage distribution network. We have done this work with Noja Power, and this work has been implemented in the Energy Queensland and AusNet's network, that is in Queensland and in Victoria. We have 100 PMUs installed at different parts of the network where there are renewable generation or there are ongoing voltage issues. And we have been given the data from the PMUs, which we could analyze, and we could try to provide some insights. That is how the renewable generation is impacting the distribution network, and whether we can use those for enabling more efficient event detection mechanisms.
Chris calling back. Hey there. Good.
Sorry. Okay. So a PhD student is working on this project, and we have considered some indices, which includes voltage deviation index or voltage ramp rate. And we have tested some simpler machine learning models such as decision tree and random forest. And we have been able to see that for this test data, the simple machine learning models can do the prediction with a reasonable accuracy. Also, in terms of the critical event performance, we have been given data for a scenario when there was a generation trip event, which happened during this 2:06 p.m. And you'll see that the voltage indices, they vary significantly after around 42 seconds here for different feeders, which were affected by that generation trip. This was an industrial feeder. And for this one, the voltage performance violated because it was not anymore within 5% as specified by the distribution network operator. So, but after some time, it came back to its normal limit. However, when for this feeder, this hospital feeder, it didn't go like that. It was 100% deviation, which basically means that there was a power outage. The voltage was zero completely at this point of time. And if we look into these trends, we can see that there was some patterns in the voltage indices a few seconds before the event. So if we can extract these patterns and we can examine these, we can use them to predict that after a few seconds, there could be a power outage happening. So this is where the PMU data and the analytics can be really useful. Another use case or application could be the energy optimization. We can try to use different optimization technologies so that we can optimize the energy consumption patterns and ensure that the peak energy consumption periods can coincide with the peak generation period. We can integrate different forecasting techniques here to perform solar generation forecast, weather forecasts, and we can tell the customers that what is the best time to turn on the different appliances. Also, we can predict user consumption pattern, and from there we can predict user behavior, and we can identify how much motivated they could be in optimizing their energy use, what could be the benefit for them, what could be the signals that can affect their energy consumption. We have implemented this energy optimization for a pilot study with Geelong households. This one was funded by the Geelong City Council, and we partnered with ITRON Australia to develop that energy optimization or algorithm. We considered 20 households in Geelong, which are already equipped with solar panels, but they may not necessarily have a battery system. Some of them have, but some of them did not, and we did not consider that in our energy optimization process. So this pilot project involved the development of the energy optimization algorithm, and we have implemented that through a Raspberry Pi microcontroller, which communicates with the smart plug and turn on or off the appliances during optimal times computed by the algorithm. And we also provide SMS notification to the users so that they can they know beforehand that when they have to turn on the appliances. This is a high-level architecture which we have used in this pilot study. The weather forecasts are generated and stored in this file server, from which the weather data is fed to this Raspberry Pi microcontroller, where we have the optimization algorithm implemented, and this computes the optimum appliance times. And these optimum appliance times are also stored in this file server so that we can use it later for further analysis. And these optimum appliance times are, during these times, the Raspberry Pi turns on the smart plug. And it also specifies these optimum times through SMS notification to the end users. This is an example with one of our participants in this project. That is before implementing this algorithm and after implementing the algorithm, how does the net energy consumption change? So before implementing this algorithm, the customer used to turn on their washing machine at 9 a.m. and dishwasher at 9 p.m. On a certain day. And after implementing the energy optimization algorithm, the algorithm computed the optimum times for operating washing machine and dishwasher as 2 p.m. and 3 p.m. when there was plenty of solar generation. And you can see the net consumption has been smaller during this time period if we compare this point with this point, you can see that the peak consumption is less and the excess generation has been better utilized in comparison to this one. So that was the benefit for the energy optimization scenario. And we can also test that with other type of appliances such as thermostatically controllable appliances, which we have not done in this version of the case study, in this pilot study, but hopefully we will be able to extend that in future to consider those kind of moves. So this data analytics can also be used for energy storage performance benchmarking. For example, the battery storages, these are now getting more and more used, not just for the residential applications, but these are also used for newer applications such as electric vehicles. So it is important to identify how the different battery chemistries perform with different battery aging and degradation. So we can monitor the battery voltage, current, state of charge, and obtain different correlations among these parameters and see how these change over time. We can use signal processing methods to estimate the state of charge for different battery chemistries, and then use data analytics to predict how the state of charge degrades over time and whether we can get some insights about the battery lifetime. We have implemented this in a use case with the ITP Battery Test Center data. So this was part of the Australian Battery Energy Storage Performance Standard Development, where we have collaborated with DNVGL Smart Energy Council, which was previously known as Energy Storage Council, CSIRO, and ITP Australia, which stands for IT Power Australia. So ITP Australia, they also got a different funding to set up a battery test center where they have different batteries, which are like system scale batteries, not just the cell level, the bigger ones. And they install them in the battery test center, do different charging, discharging, and monitor how their voltage, current, etc. changes. In this project, we could test a number of commonly used battery chemistries, such as nickel, manganese, cobalt, lithium iron phosphate, lead acid, lead carbon, and see how their performance change over different temperature, different charging, discharging rates, and so on. And these insights are used to develop the capacity estimation algorithms to more effectively predict the battery capacity degradation. So how this testing has been done in the ITP test center, each battery pack is charged to over 3 or 4 hours to emulate daytime charging, and then after a short rest period, it was discharged for another 3 to 4 hours. So each battery undergoes 3 charge-discharge cycles on a daily basis. This is an accelerated charging-discharging because in a usual residential scenario, you'll have 1 charge or 1 discharge cycle. But because we want to see the capacity degradation during the project lifetime, which was 2 or 3 years, that's why it has undergone an accelerated charging cycle. And the battery parameters are monitored with 1-minute frequencies for the years between 2016 and 2018. So these are the left side figure shows the different state of charge profiles for the batteries. You can see that the lead carbon and lead acid batteries, they have not discharged deeply. This is to stay with the manufacturer specifications, but if we could discharge them deeper, there could be more insights developed on these batteries, whether they can sustain those kind of scenarios or not. But we stick with the manufacturer guidelines here. And then we calculated the discharge capacity. So we have calculated how much time does it take for a complete discharge, and then after that, how much time does it take for a complete charge cycle to get to the same state of charge level, and how does that change over different discharge cycles. And we have seen that with the number of cycles, the NMC and the LFP batteries, they have a better retention of the capacity, whereas the lead acid and lead carbon, they're having a capacity degradation. And these results are from this conference paper back in 2019, but some detailed analysis of these results have been also here in this extended version through the journal paper, which was recently online. You can also have a look into that. And apart from that, there are newer applications such as peer-to-peer energy trading. So if you're not familiar with this peer-to-peer energy trading, it considers a local market where we have some houses with solar panels and or storages. And these users, they can sell or purchase the energy among themselves. So the financial settlements can happen among themselves, and the actual energy exchange can take place through the built-in distribution network. So this can form a peer-to-peer energy market where our focus is to make sure that the supply-demand balance can be achieved in an optimal manner, and users can achieve their profit savings margin. We can set different priorities for selecting buyers and sellers, which can be based on the distances, prices, energy demand. For example, we can say that the users which has smaller distances, they will be preferred or prioritized compared to the other houses. In these scenarios, we can use data analytics to develop some insights on the energy use patterns, and these patterns can be helpful in identifying what should be the load shifting or pricing strategies that the sellers or buyers should use. So we have, this work was done by one of my master's coursework project student. We have considered the Ausgrid home electricity data set and used 6 houses from there to collect their generation and demand data. We assumed that among the 6 houses, 2 houses have solar panels and storages, 2 houses has only solar panels, and there are 2 houses which do not have any. In this work, we have made this assumption that houses with smaller demand are given higher priority because we were considering the fact that smaller demand houses may have that for critical load. We also considered 25% load shifting with all the 6 houses, where 25% of the load has been shifted from 5 to 7 p.m. to 9 to 11 a.m. when there are more renewable generation. And then we investigated how peer-to-peer trading can further improve the energy supply-demand balance in this case. So the left side figure shows the scenario before trading, and the right side shows after the trading. There is not much difference during this evening time because there was no excess generation. But if we look into the morning time, we could reduce this, we could utilize this excess generation more effectively and reduce this peak consumption if you see these timings. For example, for house number 1, at this time it was 3.5 kilowatt, whereas this is 2.5 kilowatt after trading. So we could reduce the energy demand during these daytime hours with the energy trading among these houses. So while we have data analytics in different applications of the energy systems, we also need to keep in mind the downsides. There could be cybersecurity concerns there. For example, there could be attackers at different points of the network and injecting false measurements or launching different attacks such as replay attacks, pulse attacks, etc., and disrupt the accuracy of the information that is used by the operating centers to make different control decisions. For example, in this case, if there are some random attacks by the attacker on the generation controller, there could be false operating points given to this generator, which can cause disruption in the energy supply-demand balance. Also, if you look into this example, if we have some energy consumption data, accurate data given from the smart meter, but then false injections are coming from another attacker, we can have incorrect measurements to the billing center, and that could result into incorrect billing and financial losses. Some of the solutions that are suggested in the literature include random keys for each session, re-encryption at the intermediate points. So this is the data aggregator unit, which actually aggregates the data from different smart meters, or even you think about any of the IoT applications across the energy systems, there will be some kind of data aggregation. So some re-encryption, if it is done in the intermediate controllers, that will also help with mitigating the cybersecurity concerns. We can encrypt individual device data with different keys. With IoT-enabled systems, this is often an issue that we use the same key for each and every device of that type. But we have to keep in mind when these IoT devices are used for critical applications like energy systems, we need to have more stricter security requirements for them. We can have deep learning techniques in the control center. We can use different methods to identify different patterns and based on that predict what if this is a normal data or if this is an anomalous data. Then physical layer security techniques. These techniques, they deal with the physical layer of the communication signals. So one example is the artificial noise injection in the signals that in the physical wireless signals that are being transmitted by the devices, so that the attacker cannot identify whether it is a legitimate signal or whether it is just a noise. So those kind of security techniques can also be incorporated to ensure that the cybersecurity concerns can be mitigated more effectively. And as I was talking with Dr. Michael and also looking into the current projects being done by the Energy Research Center, I was thinking about some potential collaboration opportunities and would like to explore these ideas or other different ideas with you. For example, I could think about like intelligent control of hot water systems, because I've seen that New Zealand has a large number of electric hot water systems, and these are heavily used, especially in colder climates like this. So if we can have some energy optimization algorithm, we can control the power consumption of these hot water systems. This algorithm can ensure that the demand peaks are avoided and we can maximize the self-consumption of the renewables. And we also take into account the lifestyle patterns of users, because we need to know when the user needs the hot water to be ready for their regular life, regular usage periods. We need to also incorporate weather forecasts, structural parameters, because not every hot water system will be similar because of aging and other parameters, where it is located, and these kind of things will also have an impact. And I believe that local city councils may have some interests to assist with a pilot scale demonstration, and we can create a case study which shows that how this can be beneficial to the house owners. Other collaboration opportunity could be in the optimum charging of the electric vehicles, because in New Zealand we have more than 80% electricity already coming from renewables. I think there is a lot of interest from the government to increase the uptake of the electric vehicles. If that is the case, then it will be a lot more difficult situation for the distribution network operators. If they're using the same old infrastructure and they have a newer load coming, then there will be some issues. And how these companies are going to manage the new uptake of these loads, for which we can design an optimization algorithm which can control and coordinate the charging of the EVs, so that the distribution lines are not exceeding their given voltage limits and so on. Even when designing this algorithm, we have to think about the human aspects, that is what should be the driving patterns in terms of distances or timings, etc., whether there is renewable generation available, and how we can avoid the demand peaks, because these demand peaks can result from other unavoidable loads such as heating. And very recently, I think there is interest of this about this opportunity to participate in the ancillary service market, because electric vehicles, they can pose as a large load, and they can also, if we can stop charging them, they can also result into some capacity for the market. So how we can use that potential and coordinate the electric vehicle charging so that the users can benefit from those kind of ancillary service initiatives and payments. We can collaborate in these kind of optimization problems. Basically, these are some of the collaboration opportunities which I could think of, but I'm more than happy and more than open to any other new opportunities, new research ideas, and we can also think how we can incorporate them in the energy research. Before finishing, I just wanted to talk about this conference, which we are going to hold in Melbourne in November 20 to 23rd. So this will be in a hybrid mode. So even in the worst case, people cannot come, we can hold the presentations in the virtual mode. But in case, if there is an interest to travel to Australia, I think this is the best time, because now the borders are open and we have the opportunity to again see each other and talk to each other. So the paper submission deadline has been extended to 1st of July. And you can read about the different topics in the conference website. We have different industry presentations or presentation-only sessions in the second day of the conference. So if there is some interest, we can also accommodate those presentation-only sessions there. So at the end, I would like to thank you for listening to this presentation, and thank you for giving me the opportunity to visit the University of Otago and discuss different collaboration opportunities with you. I will be available from 21st to 24th June on the room 112 in the Science Building 3. If you are interested in collaboration, discussing different collaboration opportunities, please feel free to come, and you can also send me an email through this email address. And here is my LinkedIn profile if you want to know more about the activities I do. So I would like to finish now and open for questions. Thanks, everyone.
Thank you. That was excellent. You provided a really nice overview of your research, and I can identify all kinds of opportunities for potential collaboration. So it's fantastic that you're being really proactive in terms of searching that out. Just opening it up to questions. I might get the back up that line so we can see.
If we do escape,
yeah. There we go. For those of you that are online, if you just want to shout out your questions, or you can type them into the chat box and we can read them out. Or question from the audience is also accepted as well.
Perhaps if I could ask a question, can you hear me?
Yeah.
Eric Pyle from Solar Zero. Why the smart meter? Our experience, we've got quite a lot of, a reasonable number of solar and battery systems that we monitor in real time, sort of every 5 minutes. We're coming up to the 9,000 or 10,000 mark now. Why the smart meter? Because what we've discovered is that certainly participating in demand response programs and so on, the solar comes and goes, the people turn on the oven on, turn the oven off. The smart meter really does not provide much useful data for participating in these various programs.
Yes, I completely agree with you, Eric. I think with just the smart meter, it may not be possible to get all these information. And that's why you may have seen that that's why we have that smart plugs and the Raspberry Pi integrated in the houses that we have implemented in the Geelong. Because that's from that smart plug, we can get that information about the appliance usage. But other than that, if you do not have a monitoring device for each and every appliance, the other option could be like different signal processing or machine learning algorithms used over the smart meter data to disaggregate the energy consumption. But again, that could also be an expensive solution. So
yeah, I guess just
I
in
think there is
response.
no single answer to that. There could be different possible solutions, but it will depend on like what kind of use case you are working on and what is the like cost benefit threshold.
Yeah. You know, we monitor the hot water and the EV charger and other bits and pieces as well, anything too with a Wi-Fi chip.
Yeah.
Other questions? Maybe I'll give one, and I think it's more of a reflective one. You've provided a whole range of different really interesting projects. I just wonder if I could ask you to step back and think about what's the most promising or exciting development in terms of matching up renewable supply and demand in that energy management context, or the most challenging or key barrier? Is it around getting better precision around algorithms? Is it about more intelligent smart grids? Is it about behavioral change? Is it about sort of different market opportunities to do that peer-to-peer storage, et cetera, et cetera? What do you think is sort of the key thing, or where are you going next, I guess?
Thanks. If you ask about the most challenging part of these projects, I can't tell like this one is the most significant. There are a lot of things. Sometimes when I work on the IoT projects, I find like the coordination of different components, that's a very difficult process. Some part of the network, it might be using this kind of protocol, this kind of communication. Another part is using another type of protocol. So coordinating all of them together and getting a single bigger picture, sometimes it becomes difficult. Sometimes we get too much involved in the little technical bits and pieces, and we cannot project that bigger picture to the end users and so on. And often like explaining to the end users what our project is going to do, that can also be challenging because there are a lot of initiatives going on and everyone is doing something. So sometimes it gets difficult to say that, okay, our project can do this, but it cannot do that, and so on. And like, not always people are interested to reduce their energy consumption. When we started looking for this pilot study with the Geelong City Council, we did not get much interest at the beginning because not many people were thinking that they want to reduce their energy consumption, or they may be doing that through another project or another industry. So it was initially a challenge, but then our study was also hit by COVID and other things. So there was delays, which can also be a factor. And if you talk about what should be the next step or what step I'm thinking about, I would say that what I'm seeing at this moment is there is a lot of interest going in the energy storage, including battery energy storage, and also in the electric vehicle space. And there is definitely a benefit there. If we can start early, we can do some pilot demonstrations of the technologies that we're talking about that optimum control. There can be some good opportunities to collaborate with the industry or with the market operators in that.
Other questions? if there aren't, I think we'll end it there. We're getting close to the end of time. But I think one of the things I was intrigued about was the university microgrid that you have. And I know we're doing quite a lot in terms of trying to use the university as a living lab. So there's some potential collaborations or idea sharing around that I'd be interested in hearing about. But really encourage anyone else that's on the call online to do get in touch over the next
week. Or you can also
Yeah.
send me an email, and we can continue collaboration over Zoom, because now we are very much used to it.
Yeah, because there's certainly a lot of overlap between what people are doing here at Otago and what you're doing there. So it'd be nice to develop those relationships.
Definitely.
So thanks again for contributing to this. It was fantastic. Just give you another round of applause.
Thank you.
And a virtual round of applause, I'm sure, as well.
If you don't mind, can we take a photo here? Or
Yep.
so
Yeah.